All right. Hi, everyone. Welcome back. Today our speaker is Ira Globus Harris. They're an assistant research professor at Cornell right now in the Center for Data Science for Enterprise and Society. They do basically a lot of work on responsible AI, responsible computing. Before being at Cornell, they were actually a PhD student at Penn, working with Michael Kurtz and Aaron Ruff. And today they're going to be telling us about their work on collaborative prediction via tractable agreement protocols. Ira, it's all you now.
Great. Awesome. So just to make sure everyone can hear me and see my screen, right? Great. Okay. I can only see Juba and I can't see the chat and my mouse doesn't work in full presenter mode. So if things in the chat, Juba, if you can tell me about them, that would be great. Right. So today I'm going to talk about collaborative prediction, and much like the title of this talk, this work was very much a collaboration between me and these wonderful people you see on this slide. I believe Myra is in the audience, so if you have any hard questions, please direct them to her. All right, let's keep going. Oh boy, now my mouse isn't working. Okay, there we go. All right, so I'm going to talk about some motivation in the setting, and then we'll talk about all of the different building blocks that together put together this result. All right, so the main motivation is machine learning in collaborative settings. So increasingly, we are interacting with AI agents to make decisions. I should say all of the visuals in this talk were made with ChatGPT. A lot of them were made by Serby, my co-author. So if you see a really clean, cute animate or graphic, it's hers. If you see something confusing, it's mine. Right, so we're increasingly interacting with machine learning to make decisions. And like you might think about the medical setting as a sort of example of this. So for instance, like whether or not to keep patients overnight or to send them home, how to triage patients in the ER, assessing what medications to use, how much insurance should cover. A lot of these things use either like traditional actuarial tools or now increasingly machine learning to make, or at least help make these decisions. And one of the interesting things about this setting is you don't really think about it as just a patient coming in and interacting with a risk predictor that's going to give them some sort of score that then maybe a decision will be made with respect to. Instead, it's a collaboration, right? Like the doctor is asking, well, should I admit this patient or not? And they might consult a risk predictor, and then together, this sort of combination of the risk predictor and the doctor are making a decision together. So the doctor could be using the prediction, but also they might be using their intuition or their personal expertise to make this decision, right? So how should we think about these settings? In particular, it'd be really good if we knew, well, will this combined system perform better than either one of them independently and under what conditions? So like in particular in this medical setting, you might think, well, okay, there's some cases where we know that models do much worse than human practitioners. Usually this is because there was really bad data practices, right? Like a COVID prediction model where the X-ray had, if the patient had COVID, they were a child, and if they didn't, they were an adult. So the predictor just learns whether or not to, a skeleton is a child's or an adult's. And sometimes it's less clear. We also have a really long line of work showing that actuarial prediction models, so this is like kind of pre-machine learning, but like giving people a simple decision rule, for instance, to help them make a prediction, does much better than people do on their own. And in particular, there's a lot of evidence in this medical setting. And then we also have newer results showing that, well, sometimes there's subsets of patients that doctors can much better diagnose than a model can. You maybe think of these as like the edge cases, right? So it'd be great to think about how can we think about these different regimes in a more principled way. That's what we're going to talk about here. And the main takeaways, in case you fall asleep in the rest of this talk, are the following. So first of all, we'll see that allowing interaction between the model that's making a prediction and the person making a prediction is very helpful and can circumnavigate a lot of the impossibility results that we have in this space. And in particular, we're going to be designing models that have really bespoke performance guarantees for this particular sort of interactive setting. And then one of the main tools that we'll rely on here is variations on swap regret. So we'll see that, designing sort of regret-like notions that make sense in this particular context is going to be very powerful. All right, so what's the exact setting that we're talking about? So here we're going to think about, say, a patient comes in, they have all of their different features, and some of those features are accessible to the doctor, and some of them are accessible to the machine learning model. And you can think about, maybe there's some features that are accessible to both, but in general, it might be useful to think about situations where they're somewhat disjoint, though it's not particularly important for the particulars of the results. Right. So in particular, there are some things that a doctor could see about a patient that they cannot communicate to the machine learning model, right? Like something, the vibe of the patient, their disposition, their smell. Like you can't communicate these things to a machine learning model. And similarly, if we think about features as being embedded in high dimensional representation spaces, there are a lot of things that the model might be able to see about the patient that it can't really convey to the human doctor. Okay, so there's disjoint features, X of M, X of H was a machine, human, MH, given to both. Okay. Now, like I said, like in a perfect world, you could just share all your features that you see. Like everyone could just have access to everything. But this is just too strong of an assumption for the reasons that I just mentioned, right? So you could say, okay, well, if we can't do that, what can we do? Well, one thing we could do is we could have the model predict something and tell the person what they predict. And the human likewise could communicate to the model what they predict about the patient, and then we could aggregate them, right? We could take the majority vote, or we could do something else clever, maybe. Like we can only do a majority vote. There's on 2 of them, but we can take the average, right? We can do lots of things. But this is too weak. And in particular, there's a nice result from 2023 from Nikhil Garg, Kenny Peng, and John Kleinberg, showing that there's no aggregation rule such that you can guarantee that doing any sort of combination of the predictions is better than either one of them for any distribution over the labels. Okay, so this is sort of a no free lunch result that says that in general, this kind of aggregation is going to have edge cases where it does badly. So what we do instead is we say, well, why don't we have the 2 agents communicate back and forth until they agree? So the risk predictor might say, I think that this is the risk for this patient, and the human doctor could say, no, I think it's this, and then the risk predictor will make an update and will say, well, given what you know, I'm going to update my prediction, and we're going to go back and forth, and hopefully, eventually, we can agree. Okay? So what would we want under this scenario? Well, the first thing we would want is this process to terminate at a minimum, right? We want the model and the human to reach consensus, ideally in few rounds, right? We want it to be efficient and not too cumbersome for the human doctor, for instance. And secondly, so okay, at a minimum, you want this system to do better than either of them independently. But an even stronger thing you could want is you could say, well, what I want is I want the decision that they make to be as good as if they both had each other's information. They actually both had access to this underlying feature space. So this is going to be our goal, and we'll try to characterize when this is possible. Right. And just to reiterate, what we really want is that we want any combined human AI system to work better than either of them can alone. Like this is the world that we want machine learning to be useful in, right? All right. So the first part of this results comes from a paper that I'm not on, which Natalie, Serbi, Varan, and Aaron wrote for Stock last year. And this is just about the problem of agreement. So what do I mean by agreement? So in 76, Oman wrote this sort of seminal paper on what we call it, now we call it Omanian agreement. And the idea is that if 2 Bayesian agents have a correct prior and they have common knowledge of the other's posterior expectation, then they will agree. What this means, in other words, is that Bayesian agents with common knowledge cannot agree to disagree. So what does this look like? You can imagine, okay, you've got some sort of, you've got a correct prior and you know what each other's posteriors look like. And the first person says, well, I think the risk for this patient is X. And the other doctor says, well, okay, I thought that it was Y, but now I know you think the risk is X. So I'm going to update my belief accordingly. And then we're going to iterate and do this back and forth a bunch of times. And eventually we're going to converge to agreement. And an original thing, like it was not clear that this could be done efficiently, right? Like you'll converge to agreement, but that could be in like an exponential number of rounds. In 92, 2 others show that if the underlying state space is finite, then agreement happens in a finite number of rounds. Right, so this is, I'll just skip these. And then in 2004, Scott Aronson wrote this really nice paper showing that, in fact, we can do this efficiently. So with high probability, we can reach close to agreement, epsilon agreement, meaning the thing you're predicting is within epsilon of each other, in terms of L1 distance, in a polynomial number of rounds. Okay. So this is a nice framework for a couple of reasons. So we're guaranteed to agree, right? We know that after we interact for a couple rounds, we're going to reach consensus quickly. And interestingly, this is independent of like the size of the state space that either agent has. So it doesn't matter if they're super high dimensional, we can still only communicate a small number of bits of information and we can still reach consensus. And like, okay, what does that mean for our setting? Well, it means that like if you only share your predictions, that's again like it's low communication and you don't have to assume anything about the features. They could be totally incompatible and incommunicable, and that's okay. And then finally, this process is accuracy improving. So you're only revealing information over time, and what this means is that the final predictions will be better than either of your starting points. The challenges with this framework are that, well, it assumes that everyone's like a Bayesian and irrational, and it assumes that you can always like update your posterior distribution. And especially if you've got a really complex state space, this could be a computationally intractable or challenging thing, right? So that's kind of the challenge there. So that, and in particular in our setting, like it's not really clear even what this like common prior assumption would mean, right? Like I don't know what it means for a human and a model to have a common prior. So the goal of this paper is to relax these assumptions, but still guarantee fast agreement. And the main result, so that here we move from the Bayesian setting to a repeated online machine learning setting. And it leverages a notion of calibration called conversation calibration to get the result. So this is, all of these results can be lifted back to the Bayesian setting. So it all applies to the Bayesian setting, but it's weaker. In particular, this conversation calibration notion is like computationally efficient to enforce. And like other notions of calibration, you can do it in a way that's accuracy improving. So what they show is that if agents satisfy conversation calibration, then they can quickly reach fast agreement. And as you talk for longer, you get more and more accurate. So this is a potential argument. All right, so what's the setup look like? On a single day, the patient would come in and they have two sets of features, one for the model, one for the human, and the human is going to make their prediction. So just to be clear, we're on a single day T and we're going to interact over a collection of rounds on that single day. So in the first round, the human sends their prediction to the model, and then the model sends their prediction back to the human, which is somehow incorporated information about the human's prediction. And it is going to continue over K rounds until ideally they agree. By agree, we mean that the predictions are different by less than epsilon. Okay, at the end of the day, they learn the true outcome, and then this process repeats over T days. So every day we have some number of rounds of interaction until you agree, and notably, like these number of rounds of interaction might not be the same every day, because it's just until agreement. Right, and the goal is you want for most of the days, you want to reach agreement in few rounds. All right, so I said that the main technical tool here is conversation calibration. What's normal calibration? All right, so calibration is the idea that predictions should mean what they say. So in other words, if we condition on the value that a prediction makes, the predictor should be correct in the expectation. So the canonical example is weather prediction. So if every day I predict how likely it is to rain, like day one, I predict 25% chance of rain, then 50%. And then at the end of the day, I, learn what the weather truly was. If I look at, say, all of the days that the weatherman predicted 25% chance of rain, it should have rained 25% of the time. It's a calibrated predictor. And similarly, if I looked at the days that the weatherman predicted a 50% chance of rain, it should have rained 50% of the time, and so on and so forth. And this is a very weak notion, right? Like even a constant predictor that predicts the label mean. I'm sorry, it's snowing out. This is very exciting. Lovely. Right, so it's a weak notion because the average the predictor that predicts the average label will be calibrated, but it's strong because if you witness in the sense that if you witness a failure of calibration, you can always improve your predictor by making it more calibrated. And it's efficient to check. It's a nice notion. What do we mean by, so we're going to try to take this notion and then we're going to try to kind of massage it to work in our setting. So there we were just conditioning on the values of the predictor itself, but there's no one telling you can't condition on other things. So the thing we're going to be interested in doing here is we're going to condition on both the prediction itself and also that you're making and the prediction of the other agent in your previous round of conversation. So for instance, conversation calibration for the human in this back and forth conversation means that for any prediction that they could make and any prediction P prime that the other agent could make, that if I look at only the rounds where my human, at round K, I look at if the human predicted round P, and then I look at all the times that the model predicted P prime in the previous round, then the bias of my predictor should be small. This is kind of hard to look at, I think. So let's look at a picture instead. Okay. So here, from left to right, we have the days in which you're interacting with patients. So on the first day, you have this patient on the far left, and you interact, the human and the model are interacting over some number of rounds. And on some days, they're reaching agreement, and on some days, they're not. Okay, so what would conversation calibration mean? It would mean, for instance, that if I look at all of the days that the human predicted around 25% as my risk in the first round, so I'm just looking at the first round, I'm saying, okay, there were 3 of the days where they predicted something close to 25%. And then I look at also all of the days that the human, or sorry, let's say purple is humans and the blue is model. So the blue is the model predicting around 50%. So if I look at this subset of days, and blue is the machine learning model's predictions, then if that machine learning model or AI is conversation calibrated, then the expectation of the outcome on those days, 1 and 3, which are the ways that intersect with both of those events, we should have around 50% be the expected outcome, because that's what you need for the bias to be small. Okay? So we'll have this guarantee for each combination of rounds, the models, level sets of the model's predictions, and the level sets of the human's predictions. And it turns out that if both the human and the AI are approximately conversation calibrated, then most of the time you will achieve agreement after few rounds, where few is proportional to these probability curves. Okay. I'm not going to go into the proof here since it's I want to get onto the second part of the talk, but it's essentially like a potential argument and relies on the fact that if you have 2 conversation calibrated sequences, you can sort of refine one by the other. Okay. So this isn't quite enough for our result. What it does say is it says that you can improve over either party working alone, but a much stronger statement that would be awesome to be able to say is if we could actually do as well as the world where everyone shared features. Okay. In other words, when can we guarantee information aggregation? So that's in the second part of this talk, I'm going to talk about that result, which is in a paper that will appear at SODA this year. Okay. So just to be clear, the setting we're thinking about here is you have access to 2 hypothesis classes. There's the humans hypothesis class that they have access to, which I'm going to call curly F sub H, and that maps their features to outcomes. And the model on the right-hand side has its hypothesis class F sub M, and that maps its features to outcomes. And what we want is that an interaction that is based on hypotheses from these classes can do well or can be competitive with respect to a joint hypothesis class that had access to both features, right? We don't need to know anything about this joint hypothesis class, but we would like to be competitive with it. Okay. All right, so we want low regret, with respect to this joint hypothesis class that's defined on the joint features. Now, you should be skeptical of wanting to be competitive with this for the following quite contrived example, perhaps. Imagine that my labels are generated as the XOR of the human's features and the model's features, and the human and the model's features are both generated by coin flips. In this case, the Bayes optimal prediction that the human can say is, well, they can guess 1/2 because their feature was generated by a coin flip, and the label, as far as they can tell, is also just a coin flip. And so can the model. So all of the information that they're going to be able to send back and forth to each other, if they're not allowed to submit, if they're not allowed to just hand the other person the feature, is just by guessing 1/2 all of the time. So they can't make improvements. So unless features are shared, which of course it's contrived because in this case it's the same dimension to share your features as it is to just share the Bayes optimal predictor, but don't worry about that. You can come up with harder examples too. In this case, information aggregation, in the sense we're thinking about, just like wouldn't happen. So clearly we need to somehow characterize when this will happen and when we're in this sort of hard example. Okay. Right. So just to reiterate, we want with high probability to agree at the end in a few rounds at the end of each of our interactions every day. And we want the thing that they agreed upon to be as good as if they directly shared their features. Okay. All right. So, right, again, right, we want that to be competitive with respect to this joint hypothesis class. And the ingredients we're going to use for this result are, we're going to characterize a weak learning condition on these two hypothesis classes that they need to satisfy with respect to the joint in order for this condition to hold. And we're going to rely on something called, what I'm going to call conversation swap regret, which we'll use to sort of give us this agreement that we need. Okay, so what's the weak learning notion? So this is a condition that is joint on the human's hypothesis class, the model's hypothesis class, and their joint class. And all it is that if there is some function in the joint class that can improve over a constant predictor, then either there must be one in the human's hypothesis class or the model's hypothesis class that can also improve over a constant predictor, where improvement is in terms of squared error. So this in particular avoids the kind of hard case that I just gave, right? And the reason is because there you have a model in your joint hypothesis class that can obviously improve over a constant predictor. Because if you have access to both people's features, you can just deterministically always generate the label. But there was no hypothesis in either the human or the model's hypothesis class that can. Okay, so it would not satisfy this weak learning condition. You can think of this as a two-party generalization of a weak learning condition in earlier work that I'm going to touch on in a little bit. That came out of the multi-calibration literature, and it's worth saying this is in fact satisfied by classes. Right, so the nice thing about this, just to reiterate, is it doesn't say, like for a particular example, you don't need both the model and the human to be good at predicting or be able to make improvements over that subset of the distribution. You just need one of them to, and then the communication will let the other person make refinements based on that and make improvements so that you're both better off. And we'll see how in a little bit. All right, the other ingredient we need is this thing that I was calling conversation swap regret. And the intuition here is very similar to the idea of conversation calibration, in particular on subsequences that are defined by predictions of the other agent in the last round, sort of in the same way that we were defining subsequences for conversation calibration. You need no swap regret with respect to the best function in your class. So in math, it looks like this, but I'm gonna show you with a picture in a second instead. Right, so here we're subsetting over both people's predictions and the people and the squared error of their models. Okay, just to review or introduce for those who haven't seen it before, what does vanilla swap regret do? So normal swap regret, you're just thinking about a single hypothesis class and you want regret with respect to it. And you want a model which, conditioning on the fixed predictions it makes, does better than any other model in the class. So what this looks like is if you imagine you have some hypothesis class F, I should say F, not H there, sorry. And let's think about it in the distributional setting for now, but you can just as well think about it as a guarantee over transcripts of interaction instead. So you've got distribution over labeled samples. I'm going to condition on the fixed predictions that my model makes. I'm going to split it into its different level sets. So I can look at all the bucket of predictions that it predicts 0 for, the bucket of predictions it predicts 0.1 for, and so on and so forth. These are disjoint. Now I can look at only a single level set of our predictor. I can ask, is there another model in my hypothesis class that can make an improvement in squared error on that particular level set? And if there is, we would say that we incur regret in this form. And if there isn't, then we do not have, then we have low swap regret. So now our definition here for conversation swap regret is the same, except instead we are not just predicating on the predictions of a single your predictor. We're predicating on the predictions in the conversation transcript, right? So here we have a level set that is conditioned on both the human's predictions at round K and the model's predictions at the previous round. And we're looking at the squared error of our human's current prediction on that level set, and we're comparing it to the squared error of their best prediction over their hypothesis class on that particular level set. Okay, so this is a definition. You would require low conversation swap regret for both the humans hypothesis class and the models. Okay. The nice thing about conversation swap regret is, well, if you have as long as your function classes are closed under constant functions, then conversation swap regret implies conversation calibration, because as long as you've got those constant functions, if you if you witnessed a failure of calibration, you would always be able to swap out on that subset with a constant function instead, and you would repair it. So as long as if we have conversation swap regret, we would have done that because it would have improved things. So they implied that conversation swap regret implies conversation calibration. So what this means is we can leverage the result from the earlier Fox paper and get agreement if we have conversation swap regret. Right, so the main result here is that if both the human and the AI have vanishing conversation swap regret with respect to their respective model classes, and their model classes satisfy weak learnability with respect to this joint hypothesis class, then agreement, which you can get because you have conversation calibration, an agreement implies low regret with respect to this joint hypothesis class. Right, so why does this work? Well, roughly, if your predictions have no conversation swap regret, then you can get external regret, meaning just like a general statement about squared error minimization. This is, of course, in practice a little bit trickier because you only have approximate swap regret. In fact, you only have approximate distance to swap regret. So you have to be a bit careful in the analysis. Right, but that's the idea. Okay, so how do you actually achieve a sequence with those conversation swap regret? Right, so what we would do, we require that the model and the human have swap regret. Okay, we've got a room booked. Okay, I didn't know this room could be booked. Okay. Okay. Interesting. Okay. Right. So we're going to require that the model and the human have swap regret respect to this joint class respectively at every round. And then within those rounds, we run this agreement protocol, which will converge quickly each day. Right. And then if they agree, that means that they have low regret with respect to both classes simultaneously. Let's take a look at it. Okay. So how do we do this? I'm just going to show it to you in the distributional setting because it's a little bit simpler. Right, so here we're going to imagine that instead of interacting over days, we have a distribution over features and labels. And in the training, setup. Both have access to their model classes, and they also both have access to some samples from their distribution. Let's say the model first has its initial model, f sub m0, and it can create initial predictions over using that model over its sample. And it can just send all of those predictions over to the person. And she has her own sample, and she has her hypothesis class, and she can generate a new model that's going to be based on her hypothesis class and the predictions of the AI agent. Okay. And she'll update, she'll generate the set of her n predictions over her sample and send them back to the model. And hopefully they can continue this process until they agree. Okay. In test time, you no longer have access to the sample, the training sample. So you're given a new unlabeled data point, and you have your like collection of models that you generated over the training process. And just to be really clear, you do have to repeat this whole interaction. So like the AI agent will generate its initial prediction. It will send it to the human. They will use their transcript from the training process to generate a second, their updated prediction. They'll send it back to the model and so on and so forth. So even at test time, you still have to have interaction. Okay, so how do we do this in the distributional setting? So the main thing we need to require that the model and the human both have swap regret. Because then if they do and they agree, then they'll have swap regret for both classes simultaneously. And then as long as the speak learning condition is satisfied, they will have external regret with respect to the joint hypothesis class. Okay. So the way we do this is we leverage a result from multi-calibration, and particularly this nice level set boosting algorithm from this paper from 2023 with myself, Declan, Michael, Aaron, and Jess. And the high level idea here is that you can get low swap regret by you take your original hypothesis and you split it into its level sets, and you call a squared error oracle on each of those level sets independent. And if you can make an improvement to the model doing this, then you're going to switch out your current model for that new model just on that level set. And then you're going to iteratively do this, looking at the induced level sets of your new predictor until you no longer are making improvements in squared error. And once you're no longer making improvements in squared error, that means you must be close to optimal. All right, so pictorially, if we start out with an initial model, F naught, we split it into its discretized level sets. And this is just like, imagine this is just the human is doing this, or just the model. We're not in the conversation setting at all, just to be clear. We're splitting a model into its discretized level sets. And then for each of them, I call this squared error oracle, and I have a new model that let's call it H1, for example, for the first level set. Right, so this is the best model in our hypothesis class, and our distribution constrained to just the points where our initial model is equal, predicting V. Okay, M of these, one for each of the level sets. Now we have to round each of the results of each of these predictors to make the level sets make sense. And now we just iterate on each of these independent. So you get like a whole tree of predictions. So how can you do this in our collaboration protocol? Start out, the AI has their original model, and they send that original model's predictions over to the human. Now the human doesn't know anything about the machine's model, but what it can do is, or she can split her sample according to the level sets of that or other model, because she has access to the predictions on the sample, right? So she can split into these K different or M different level sets according to what the other person prediction. Now for each of those sets individually, she can run this level set boosting algorithm that I just told you about. And this will guarantee that she has low swap regret with respect to her own hypothesis. Now, she'll make sure at the end of each of these runs of LS-boost in parallel, whether or not it did actually substantially improve squared error. And if it did, she's going to use its output as her prediction. And if it didn't, she's going to swap out her predictions on that level set for the predictions that the AI model used instead. Okay. At the end of this, she'll have some sort of composite predictor that's made up of a lot of different predictors from her hypothesis class, as well as maybe in some cases the predictions of the other players. And she can send back those predictions to the model, and it can run the same process. So this will happen over R rounds, but every internal sub-call in the level set boosting algorithm is improving squared error. So every single thing you're doing in this process is improving squared error. This means that eventually you have to stop, because eventually you will have driven your error down. And in particular, not only will you stop, but because if you aren't making improvements in squared error, you're swapping out your predictions for the other player's predictions. This means that you must agree. So that means that you get low swap regret on both your own hypothesis class and the other person's hypothesis class. I forgot to switch these to Fs. Sorry. And so if they both satisfy the gamma weak learning condition, then you'll have low swap regret with this joint class. So that's really nice. So it's like a pretty straightforward construction, and particularly in the distributional setting. In the paper, we also talk about the action feedback setting, and again, you can lift all these results to the one-shot Bayesian setting as well. I also wanted to mention, so connecting this back to the related work, one kind of nice thing that I alluded to earlier is that I think this shows that in some sense interaction is really useful, right? Means that we can, a lot of these works on complementarity and collaborative learning have these no free lunch style results showing that you can't do that well in all contexts, which is like a bit of a bummer if you want to advocate for like leveraging human expertise. But this shows that interaction can really help. Speaking of leveraging human expertise, so this one result in the medical context that shows that you can sort of figure out where humans are in fact doing much better than models are. You can think of what we're doing here as a multi-round version of what they're doing there. Which is essentially they're looking at like all of the predictions that are indistinguishable for the model, and then you look at how the humans behave differently on those subsets. So here, we're doing something very similar, except for in an interactive fashion. Right. Here we have either only one or no distribution, which is different than sometimes these contexts we're thinking about like multiple data distributions. Right. And a lot of these results have relied on decision calibration, cross-calibration predictions. Right. There's also this other line of work on information substitutes in the Bayesian setting. And here we have a weak learning guarantee or requirement that's a bit weaker. So what are the takeaways? First of all, simple interaction works. So you can exchange only predictions or just actions even without your features to have efficient collaboration. You don't need Bayesian rationality assumptions. And you can get information aggregation via agreement under relatively natural representation. Swap regret was used for this. Oh, I thought I had one more slide. I guess the other thing I'll say is like as a meta takeaway, I think that the emphasis on interaction is really interesting. In particular, if you want to like advocate for a world where human expertise is valued and taken seriously, this is like one setting where we can say like, if you allow people to, if you interact with models, we can maybe really leverage this. And I like that, I guess, as sort of meta. All right. Questions?
Well, I mean, before taking questions, first let's thank Ira again for the talk. It's Great. Yeah, so anyone has questions? All right, let me thank you again, Ira, for a great talk.